Welcome to our talk on Towards Learning Terminological Concept Systems from Multilingual Natural Language Texts by me, Lennart Wachowiak, and my co-authors Christian Lang, Barbara Heinisch and Dagmar Gromann, all from the University of Vienna. So first I will provide you some background information for understanding this presentation, with the first question being what are Terminological Concept Systems, or short TCS. And mainly TCS consists of concepts which are abstractions of a set of physical or abstract entities. This will get a bit more clear on the next slide when we have an example. Secondly, there are the terms, which are the concept's designation by linguistic means. And lastly, the relations between concepts, which are either of hierarchical or semantic nature and give structure to the TCS. So now as an example, we have here the concept simply defined by the ID C1 with a single term, COVID-19. But one concept can have multiple terms which are synonymous. And one of these synonymous terms would be coronavirus disease 2019. And what you can see here as well is that a term doesn't need to be a single word, but it can also consist of multiple words. So a concept can stand in relations to other concepts, and for this we defined our own set of relations based on an extensive literature review, looking what other researchers and people did, and creating a set of relations that made sense for us and for which we could create training data as well. The most important of these relations, giving structure to the whole TCS, is the generic relation, as it sorts concepts hierarchically, and it is a relation. So COVID-19 is a virus. So we gave it the generic relation in this example. Then to the semantic relations, there we defined the causal relation, and an example for this is COVID causes cough or coughing. Then we have spatial relations. So maybe this TCS is based on a text about COVID in Europe. So we have a spatial relation between COVID and Europe. Then we have another hierarchical relation, which is a partitive relation. And Germany is a part of Europe. Then we have the origin relation, with an example being the BioNTech vaccine, which comes from Germany and was developed there. Then we have the instrumental relation, so the vaccine is an instrument for containment, for containing the virus. And what also was added now to the TCS is the associative relation between COVID and containment, because there is clearly a relation between these two concepts, but it doesn't really fit into any of the other categories we defined. And associative relation is also the only one which is without direction. As you can see, it has no arrow at either end. And lastly, we have the activity relation, with the virus having the activity of infecting people. Now, what do we want to do? In our project, we created a system called text to TCS, which, given natural language texts, creates such a terminological concept system automatically. So this whole pipeline consists of multiple steps. So first the texts are pre-processed, then the terms are extracted. Thirdly, between the extracted terms, relations are identified. And lastly, this whole combination of terms and their relations are built into a TCS. And this whole pipeline will be explained in more detail. But first, to the motivation, why do we want to have an automatic text to TCS system? Well, one reason is that specialized communication needs to be able to rely on a consistent usage of terminology by different parties. So politicians, researchers, and journalists might all use the same terms, but they also should use them in the same way. So a terminology concept system can help with making clear what a specific term or concept actually means. And a TCS alleviates that problem, but manually creating one is very cumbersome, which is why we want an automatic approach. And lastly, we also offer a And lastly, we also offer a contribution to the linguistic linked open data community by exporting the created TCS as TBX and in the future also as RDF. So now to the method. And before I go into detail on the models we actually use, some background knowledge on what type of neural network we used. We used so-called language models. The most famous one, which you probably have heard of, being BERT. And these language models are deep neural networks, which are pre-trained on the task of predicting a word given its context. So for instance, here in this example, we have the sentence, LDK is my favorite mask. So the mask needs to be predicted by the model. So hopefully it would predict, if it's trained enough, the word conference in this case. And for this task, there are a huge amount of training data available, as we can just take any amount of books or sentences from the internet, feed it into the model, mask out specific words, and let the model predict. And thus the model is able to learn very rich and contextual word representations. After the pre-training stage, these language models are fine-tuned, and by this we utilize the rich encoded knowledge by making use of exactly the same neurons, the same weights and so on, but just changing the final layers to fit our specific task. So a very famous downstream task is, for instance, sentiment analysis, where we want to say if a sentence has positive or negative sentiment, and then we train the model on this task, needing not so much training data anymore because the model already encodes a lot of knowledge from the pre-training phase, and then a sentence like, what a nice presentation, hopefully would be classified as positive. Now, in our case, we don't need sentiment analysis, we need term extraction and relation extraction, which can both be done via language models. And we don't take BERT, we take a multilingual variant of BERT, which is called XLM Roberta. And Roberta is a slightly improved variant of BERT, and XLM Roberta is a multilingual variant, which was pre-trained in over 100 languages. So if we train it with English training data, we can also hope that it will perform quite well in any of these other 100 languages. And in our case, we fine-tuned it on tagging these individual tokens as either term, part of a term, or no term. So if the sentence starts out as COVID-19 was first discovered, then we hope that COVID-19 would be tagged as a term by the final layer of our model, while the others would be tagged as no term. So for term extraction, what datasets did we use? We used two different ones. The first one being the ACTER dataset, which exists in 3 different languages, which are English, French, and Dutch. And for all of these languages, we have text in 4 different domains. And we also have a baseline due to the shared task term eval 2020, which we can compare our resulting model with. And then we also have the dataset ACLR-Detect2, which only exists in English and only covers 1 domain, which is computational linguistics. But it has the advantage that it has a high quality inline annotation compared to the simple term list given by ACTER, and it was annotated by 2 different domain experts. Now to the relation extraction, we again used XML Roberta, but this time giving a classification based on an input consisting of 2 terms and a contextualizing sentence, and the output being the relation type that exists between these 2 terms given the context. An example of this is an input consisting of the 2 terms COVID and cough, and then the contextualizing sentence COVID causes a cough, and we hope the model would predict a causal relation, as you can see on top. Then again, which data did we use? So in this case it was a bit more difficult because we defined our own relations, so we had to map existing relation extraction data sets to our defined relations. And for this we used SAM-EVAL 2007 task 4 and 2010 task 8 for various semantic relations. we used WCL 1.2 for generic relations, and we automatically annotated the terms appearing in the ACTR texts with generic and synonymous relation using WordNet. And lastly, we manually created some samples, especially for acronyms, because this was not covered by any of the datasets, and for no relation samples, meaning samples of two terms and a contextualizing sentence where the terms are in no relation to each other, which of course is also important for the model to be able to identify. Otherwise, for any term pair, there will be a relation extracted even if none exists. And these are the resulting statistics of the dataset combined of all these different data sources. And we can see it's quite unequal in a way, with especially associative and generic relations being quite abundant, while other relations have less than 500 data samples. And we will also see how this impacts the final training results. So now to the overall pipeline. We know what the individual models are, but how does this look in a full architecture? Well, first there's a pre-processing step where we detect the language and split the input text into single sentences, as the models only work with individual sentences as input. Then terms are extracted based on these individual sentences, feed one after another into the term extraction model. Then thirdly, relations are extracted based on the term pairs per sentence. And as a last step, we do some post-processing where we filter out certain relations and we merge synonymous relations into concepts and map the relations which before were just identified between terms to a concept level. So what are the results? On this slide we can see the results of the term extraction model on the ACTR model. And first we look at the results on the English test set, where we beat the previous state-of-the-art performance by 12 F1 score points. We also trained the model with the different available languages, being English, French, Dutch, and all of them combined. And we see that the best performance for English test language is achieved by training with English, but also by training with Dutch. And we can also see this for the other test languages. For instance, for French, where the best performance was achieved by training on English. And we also beat the previous state-of-the-art, this time by 9 F1 score points. And lastly, for Dutch, where again the best performance was achieved by training in English. And here the previous state-of-the-art is beat by quite a large margin, as the previous approach didn't rely on very up-to-date neural networks. Then the results on ACL RDTech2, which are a lot higher than compared to the results on ACTR, with an F1 score of 75.8 for the annotations of annotator 1 and 80% for the annotations of annotator 2. And we assume that is due to the cleaner inline annotation and also an overall more consistent annotation that was created by domain experts. And lastly, for the term extraction results, we also see that the performance is a lot better for single terms compared to multi-word terms, as the F1 score for multi-word terms drops around 30 F1 points, which, well, is quite a lot. Now to the results for relation extraction, we achieve a precision recall n-weighted F1 score of 87%, with only very few relation types falling under a F1 score of 70%, and those are the ones that suffer from small amounts of training data. Now, lastly, to the discussion, starting out with some limitations of our work. And first of all, the limitations of the term extraction. We only provide the model with a limited input, being one sentence, which might lead to the problem that terms are extracted which do not fit into the domain of the overall text, because the single sentence doesn't necessarily have to cover the main topic of the whole text, but can also diverge into different side topics, which might be not too relevant, but here terms, domain-specific terms, are still being extracted. Then we have the relation extraction, and one of the biggest drawbacks right now is that only relations between terms that appear in the same sentence are extracted, while those appearing in different sentences we cannot identify the relations for. And secondly, the matching of the relations from the existing dataset to the ones we defined did not always perfectly work, and there might be some semantic inaccuracies. And regarding the pipeline overall, we have chosen a pipeline approach, which of course means there's some error propagation, which means that if we extract wrong terms in the first step of the pipeline, there is little hope for strong results in the second step, where the relations are then extracted based on these wrong terms. So what's next? What did we do since we submitted this paper? What do we plan to do in the future? And first of all, we already created a new dataset with joint annotations of terms and relations, which allows us to better evaluate our models with the now manually labeled gold data, and it allows for the development of models which extract terms and their relations in a single pass through, making the overall pipeline much faster and preventing error propagation. Secondly, we are interested in extracting global relations, and therefore we already created a model which is able to classify terms without any given context. The missing context, of course, leads to a worse performance. On the other hand, it's able to classify terms which appear on the opposite ends of an input text. And secondly, we want to experiment with language models that allow for larger input sizes, like Big Bird Pegasus. Thanks for attending our presentation, and we look forward to answering your questions.